go ahead and get started. Good morning. Welcome to the second annual Southwest Research Institute and Practical Engineering for Projects presentations. This year is different because we're going to have different rounds. So this is round one this year. We're going to continue. I really want to thank the mentors here for spending the time with us. Very busy people. Tough time of the year for them. There's a lot of stuff going on for the end of the year, so I really appreciate you guys here being here. Sorry. Okay, so we got 6 teams, 6 mentors, and there are real-world projects in the areas of mechanical engineering, chemical engineering, electrical engineering, robotics and automation, thermodynamics, CO2 capturing, and hydrogen production. A lot of things going on here in this project. That's super amazing. Each team will have a maximum of 20 minutes to present a project, and after the presentation there will be 10 minutes for Q&A. I am letting you guys know that we're flexible with that. I really want for you guys to be able to present your project. Okay, I don't want you to have that rush. Obviously, we need to end before a certain amount of time, but I factor that into our schedule. Speaking of that, our schedule goes, electric toy is going to go first. Again, don't worry about it, we're a little behind, but that's okay. CO2 capture is going to go second. Low emissions vehicle is going to go third. We're going to have a short intermission here. Let the mentor stretch your legs and whatnot on you guys. And then we'll continue with the agricultural rover, the hydrogen cell, and last but not least, the cooling data center. Okay? So, again, I want to thank the mentors for being here and our panel members. In order, alphabetical last name, so we don't have any, well, you got first than me. We got Mr. Andrew Earls. He's a research engineer and process engineering and energy resources at Southwest Research. A little different. We got Mr. Eloy Flores III, Director of the Chemical Engineering Department at Southwest Research Institute. We have Mr. Michael Hartman, Manager of Research and Development at Southwest Research Institute. Internet is amazing. Miles Sala, Scientist, CCU, Carbon Capture and Utilization Process Development at Southwest Research Institute. Mr. Peter Schmidt, Research Engineer at the Chemistry and Chemical Engineering in Southwest Research Institute. And last but not least, Mr. Dr. Edmund DuPont, Principal Engineer, Intelligence Systems Division, Artificial Intelligence Department at SWIRI as well. Unfortunately, Dr. DuPont had a family death, and so he had to leave out of state. He sent his regards and a lot of good feedback for his students, and so he's looking forward because the project is going to continue on after the break. So looking forward to joining us again. Okay, housekeeping items. This is going to be very fluid. It's going to be very relaxed. There's not going to be I'm not going to be with a timer. Oh, you got to finish by this time. There's going to be people coming in and out. Okay, so just don't worry about that. We will get interrupted by the PA system for tardy roundups, and pretty soon the Pledge of Allegiance. We just handle that accordingly. Let's just have some fun. If there's an emergency, we all get together and we're going to evacuate this door through the set of stairs, but same stairs that you guys came in, and then just follow the crowd. We're going to go to the courtyard and on to a parking lot. And of course, restrooms for you guys will be in the faculty office, which I'll show you where it is. Okay? Any questions before we get started? Well, let's get started, guys. First team is going to be the electric toy. Yes.
Yeah.
Right in the front.
Good morning, everybody. My name is Samantha Mitchell.
And I'm Kyle Jackson.
And this is our electrical toy final presentation.
So I was the lead for all electrical based design for this project.
And then I was the lead mechanical engineer for this project. Today we are going to be going over our problem, our research, our solution overview. We'll go over our Gantt chart, our calculations, the electronics in our project, construction, testing and reflection, setbacks, next steps, market opportunity, impact, recap, and sources, and then at the end we'll have time for questions.
So the problem we're trying to tackle right now is that cerebral palsy is a neuromuscular disorder that inhibits certain communication between the brain and the muscles. This can lead to impaired motor skills due to, again, poor communication, which can lead to poor grasping of objects or walking, which is mainly what our project aims to tackle: walking, shifting weight between the feet, and building those motor skills.
So some existing market research, the problem with existing solutions is that they are extremely expensive, ranging thousands of dollars, and they're not adjustable for different ages or sizes. On top of that, most of the therapy devices are stationary, so they're bolted into the wall or ground, which doesn't allow for easy movement. They're not accessible to small clinics or families because they are so expensive and very bulky. On top of that, they are occasionally too supportive, so they don't allow for weight-bearing practice. So once you reach a certain threshold of movement, you can't really go past that.
So our solution for this is creating a 3x3 frame which will suspend the child to and then aid them in the shifting of their weight. It will have a button that the child will step on, which will give them the information of whether or not they're putting the proper amount of weight onto the button and give that information. So, yeah.
Okay, so this is our Gantt chart. It's what we use to stay on track throughout this project and meet all of our deliverables. These 2 weeks we were halted on construction because we were waiting on our materials to show up. So these are the calculations we did for the tension of the bungee cords. So our goal was that the bungee cords would suspend about 20% of the child's weight. And so we used weights ranging from 10 kilograms to 30 kilograms, which are the average weights for our target age range, which is 2 to 7 years old. Children with cerebral palsy are typically under the average in both height and weight, so that's why our ages are so broad. So, and we were able to, through our calculations, we were able to find out that each cord needs to have a tension of 20.1 newtons. And then these are our calculations for the pin shear capacity. So a big component of our design is that it's height adjustable. So as the child grows, or if it's in a physical therapy office and you have different kids of different sizes, you can adjust it to their height. And so, because the vertical pillars are adjustable, we needed a pin that would be able to handle different dynamic motions. And we were able to find out that using a 5/16 bolt would be more than enough, would have more than enough capacity for this project.
And so, to determine the best material for designing this button that the kid will step on, I used the flexural modulus to determine what would be best that would deflect the best under the weight of the kid. So flexural modulus, for those who don't know, is just a component of materials that, based on the dimensions as well as the material, tells you how much a material will deflect under a certain load. And so through that, we were able to find that making a button about the size of the kid's foot, 75A polyurethane would be the best material. That it has a deflection of about 2.4 centimeters, which is greater than the distance between the two electrical contacts for the button. Going to electronics, again, it is, I think, pretty logic-wise, it's pretty simple. So it just gives the kid the information whether or not the button is pressed. It's two electrical contacts that are on this plate right here. When the kid presses on it, current's able to flow from the bottom plate with no current currently flowing through it to the Arduino Uno, which will then give the information that the button is pressed, which will deactivate the LED, because the LED is currently on, so it will deactivate the LED, tell them that they have applied enough force to deflect, to press the button and turn off the LED.
So our construction process for this project, we started off by cutting our wood from the shop, and then using half lap joints, we joined the top and bottom squares, and then we drilled those into the separate vertical pillars, which then were connected by the pin. We 3D printed the corner braces for the bungee cords, and then we constructed the button. This is a video of testing we had. So as you can see, the subject is picking up their foot to press the button, which turns off the LED, and then it turns back on after the button is no longer being pressed. And then now the kid is trying very hard to sit on the floor, but because the tension cords support about 20% of his weight, he is unable to, which is important because we wanted it to act as a fail-safe, so that way the kids with cerebral palsy would not be concerned about falling, because a lot of them have developed a fear of falling, and then they don't want to practice. So this is our solution to that. This is a time lapse of me height adjusting the structure from its tallest to its lowest. It does take about 5 minutes in total, that's because it's manual. Yeah, so it took me about 5 minutes. As you can see, I have to unscrew each individual pin and then adjust it height-wise and then screw them all back in. So our reflection how's going to go over our reflection during the testing?
So I guess the main part of our testing that we want to improve upon is that although we saw that our tests were successful in supporting the kids' weight and the button working to give them that information of if they're putting enough weight onto the button, we found that the frame as well as the button move across the floor. And when the child is just moving around, we don't want the frame to be shifting at all, or the button as well. So to improve upon that, we plan to add rubber stoppers to the bottom to keep that shift, or having some sort of faster to the ground to also stop the shifting from happening.
So some key setbacks we experienced in this project was that a lot of the wood we used was warped, but you can't really blame the trees. That's Home Depot gets their wood from. So to combat this problem, we made braces that go on the outside of the two vertical posts to keep them together. And then on top of that, we had a really big material delay. Our polyurethane took almost 2 weeks to get here, which is the top part of the button. So we were waiting on that, which is why construction was delayed.
So for next steps, we wanted more robust design with aluminum telescopic rods to again be more sturdy, as well as improving the button through using load cells to give them pediatric doctors force information on like how much weight is the kid applying to the ground, and they'll be able to find out over time how the kid's progressing if this is a good means of therapy for these children.
And then, so the market opportunity for this device is actually huge. So the global pediatric mobility market grows about 7% annually. On top of that, there is a huge customer need for this type of device because current solutions are extremely expensive and not accessible for small clinics or families. On top of that, our device is more accessible both financially and physically. The device itself is actually quite lightweight, which makes it easy to store the device when you're not using it and move it around. On top of that, it's a strong fit for pediatric and occupational therapy clinics, schools, and early intervention programs and families.
So for impact, we think there is a big market for this project. It's much cheaper than the current on-market physical therapy devices for people with cerebral palsy or difficulty walking, through its cheaper cost as well as being portable and adjustable for different age ranges. So we think that there's a lot of value in the continuation of this project if we improve it.
So today we covered our problem, research, our solution overview, our Gantt chart, the calculations that we did going into this project, our electronics, construction, testing and reflection, setbacks, next steps if we were taking this project a step further, the market opportunity for this solution, the impact of our solution, and then this is our recap, and next slide will be sources, and you will have questions. So these are some of the sources we had. And yeah, that is all. Thank you guys for listening to our presentation. Do you have any questions?
So with the structure of the frame, it looked like when you were lifting it up in the time lapse, it kind of was a little wonky looking.
Mm-hmm.
Did you ever think maybe to like cross brace some of the sides to help prevent some of the like shiftiness? Because if you're building like a square cube, you can kind of push and pull on the corners. Or is that not a problem?
That's not much of a problem. So we don't really see it shifting at the corners, especially because at first I built each of the squares and then I connected it to the vertical post. So the squares do a pretty good job of keeping the vertical post stationary. The only problem is, or in line, but the only issue that we did experience was that because the winds work, some of the vertical pillars connected to the top square go out or sideways. So that's what we use the braces to correct. Any other questions?
You guys are more than welcome to
Yeah, we would love for
play,
you guys
touch.
to.
Don't put the harness on.
I'd love to show you guys the button if you would like.
Yeah, if you can pass that around.
We can.
Or is that, is it not?
No, yeah, we can pass it around.
So on the top plate, current is flowing through it, and then there's another pin on the bottom with metal foil on it. And then so when you press it, it creates a circuit tone that you're going to turn off the LED. It'll put it on light. Because it has enough screws of the proper size, so it's not fully fastened.
Gotcha.
It's awesome. That's a discount.
Yeah,
That's a
All right.
it's our WD. You guys can press the button. It turns off the LED.
So this is just to verify that the child is actually putting enough weight on the ground right now? Okay.
Well, you kind of didn't say it, but there's a broader inspiration for this design too, which is.
Oh, yeah.
You ever played the game Dance Dance Revolution?
Yeah.
Based on-
So it's somewhat of a scaled down version. If we were to continue this project, we would do more buttons and create a pad, and so then they'd essentially be supported while playing Dance Dance Revolution.
See, I just press this.
Yeah, go for it.
Honestly, you might make slower down some.
That's, yeah, I mean, that's impressive. She'll set the bar high for everybody else. What is the, did you investigate like the market? Like how hard would it be to, what is holding people back from buying something like this?
So we didn't really do, we weren't able to do a lot of research into like how to market a solution like this, but we do know that existing solutions are not very in line with the market.
Yeah, so like there's like no suspense on from the ceiling with like a bunch of these supports, like which isn't really accessible to like people at home.
Right.
Certain.
So yeah, it definitely has strong potential to be adapted into the physical therapy and occupational therapy for the people.
So it's like a cost prohibitive. It's basically a cost prohibitive technology for the average person.
Yeah, so a big issue with current technology is that because it's so expensive, families aren't able to access it, and the biggest way to see improvement in people with cerebral palsy is to catch it really, really early, and they're not able to do that because they can't afford it. And then on top of that, like physical therapy is expensive, and occupational therapy is expensive. So this solution aims to address that because this is something you can have at home. This is something you can build at home. So yeah.
Yeah, I think it's great. I'd like to see it go forward. Let's get to some session.
I guess as the child grows, would you just get different bungee cords?
Oh, yes. Thank you for bringing that up. So the bungee cords, you can actually take them out and put them back on. So if you're dealing with a kid who needs more support, so our solution was designed for 20% of their weight being supported. But if you have a kid that has lower or is lower on the mobility spectrum, you can increase the tension of the bungee cords or decrease the tension because they're actually interchangeable. So, yeah.
Then are the corner brackets of the bungee cord mounts are those, I think you said those are to be printed, right?
Yes, as
So-
well as the braces.
Okay, so if you were to go further with this one, you would recommend like a metal support or would it just say plastic support?
That's a good question. I think that going forward, I think our big, first next step would be definitely integrating metal telescopic rods. But then metal pieces obviously would be better for construction, so we'd have to look into that.
Do you know the maximum weight?
Yes, the maximum weight with calculations, like the safe load, is 30 kilograms. can probably hold slightly higher than that, but it's just, that is our safety. So, and then we did all of our calculations with a 3 and then 5x safety factor. So theoretically, it could hold more weight, but it probably should not.
I know some people that do PT stuff, so I'll talk to them about it.
Project proposal for you.
Yeah, for those of you that are new on doing this, you can provide feedback to what you liked about the presentation. I mean, it doesn't have to be questions, it could be feedback.
Right.
So whatever you guys want to comment.
Oh, that's a good point. Well, I thought, so I wrote some feedback here and you'll get it, I guess, for this, but, yeah, I thought great purpose, right? This is a great, I don't know what you want to call it, initiative, endeavor, whatever you call it. Because you're right, the cost, especially nowadays, like Medicare and all that, you know, people are debating, is Medicare, or is medical access a right or a privilege, right? Unfortunately, in our world, it's more of a privilege than a right. So giving more people access to these type of things, that's a great thing to be going for. Your presentation, the font sizes were beautiful. It was nice and clear. Like I could see it from here. The video support was great. That was just amazing. Mechanical calcs, the things that you thought about. I mean, there's probably a few other little ones that maybe you would still have to do as a mechie or whatever, but overall, those are the big ones that we would look for, like for building a plant or whatever. We consider a lot of those things. And there's, believe it or not, there's engineers that have 4-year degrees or even PhDs that don't consider physics. And then it breaks the first time. So that was a great job. The design, the adjustability of this thing, the troubleshooting, like you evaluated, like, hey, this was kind of a problem with sliding, whatever. Being able to document that, notice that, and come up with solutions or ideas to improve it. That's great. Yeah, that was awesome.
This was my take, so I feel like I was going to provide a feedback. No, I don't have a lot. Yeah.
Sorry, I covered. You guys can see.
Are we good? All right, give my hand again. Okay,
Yeah.
next theme is CO2 capture.
Let's, yeah, we can move it. Okay, where you got it? I don't know. You got it?
About 5 minutes, maybe less to set up.
Yeah, it's a little bit.
They sent it to me.
But like,
Yeah, we'll just let the mentors finish. When they give me the thumbs up, then we'll start.
Disney World?
Oh, Disney World?
Yeah, for a chain.
You guys give me a thumbs up when you're ready for you to start.
CO2 capture project that I'll be presenting today. Unfortunately, Caitlin couldn't be here with me today, so show must go on. Alright, so quick look at the agenda. We're gonna go with a brief overview of me, along with the project objective, the statement, the Gantt chart that we did, any initial research, including the liquid and solid solvents absorption that we had researched, brainstorming, our first design along with its tests, corrections that we made toward our second design, setbacks towards that second design, and further research that we conducted to finally get the third design, the second test, calculations, and eventually the conclusion. Alright, so this is me, Caitlin. I did most of the design work and any calculations. Caitlin did, for the most part, any research and the slides. So, our project objective, we quickly brainstormed and analyzed CO2 capture, specifically through direct air capture. From then, we went through development to create a device which basically showed a proof of concept of how CO2 capture works, and our end goal with calculations to prove how our design shows that how carbon is captured without really being able to capture the CO2 directly from the air. So, problem statement, a lot of problems with CO2 being in the air, of course. It being a greenhouse gas, it creates a lot of climate. It is a problem and introduces climate change, and so CO2 capture is being researched to help solve this issue. And so, unfortunately, due to some limitations of the classroom environment, there's a lot of limitations. There's not a lot that we can do to really design a model or anything like that, and I will explain that further. So we did a model to simulate that carbon capture process, which again I will eventually show. This is a look at the Gantt chart. You can see we're all located down here, downward spiral, little ups and downs between the CAD design, looking at the first design, second design, third design, and the testing and calculations towards the very end, and of course the final presentation. So this is the initial research, what we started at the very beginning. We looked at two different types of carbon capture absorption. We looked at liquid absorption and we looked at solid absorption, and the main major differences between those two. Liquid absorption primarily uses amine-based solutions derived from ammonia, and essentially in this particular model, fan brings air into. I'm so sorry. Air is brought into this cube, which but the amine-based solution introduced by these holes up here is sprayed down, which the CO2 then is then absorbed into the solution, goes down here, and into a different area where then that is treated, heated, and where CO2 is then split off from that solution, where then the solution can then be repurposed. Solid absorption works similarly, except it's more of a manual process, where it is mainly composed of zeolites, from what we researched, where it is a very porous material where the molecules of the CO2 get attached to the filter, but any other molecule mostly passes it. So then the CO2 is then captured and again transferred into a different area where then it is treated and heated, where the CO2 is then stored. And that's where we get into this infrastructure we use to save cost, because CO2 isn't a very economically efficient way of capturing that CO2. So by using existing infrastructure from pipelines and the oil and gas reservoirs, we're able to store CO2 safely without having to have high costs for drilling underneath the ground and having to store it underneath there as well. So we looked into that as well for our research. Another brief overview of the liquid and solid absorption. Liquid absorbents, again, mineral-based synthetic absorbents that take in CO2 and capture it release CO2-free air through the top of that fan. Regenerating the absorbent is heated at very high temperatures, like I explained. There is an option to use both, however, that isn't as common. But then we also have the solid absorbents fan as well, and both models they have a fan, which shows the drawing in of air, which is then absorbed. The filter then absorbs the CO2, and almost the same process, very high temperatures. Again, as I explained in the previous slide, that the filters have to be manually removed for them to be heated. And so brainstorming, we were introduced to some ideas, specifically at first with this ChemCube carbon capture device, an annual student competition that is hosted where students come up and design a device that captures CO2 or purifies water. And that, of course, helps real world solutions. And we originally were going to try to take inspiration from that device. But then we later on moved into maybe something a little bit different with something similar as in the first model with the solid absorption, but the same model as the solid absorption, where it has a filter instead. But we found that a lot of what they use is kind of like toxic, and so we couldn't really make the model like we wanted it to. So we ended up going with kind of a juice absorption with the liquid solvent being just water. It's very safe. And so, and as an example, we use this bubble column, which introduces the air through these tanks through a sparger, which is similar to what I have here. And that sparger, it introduces bubbles into the column, where then the CO2, any CO2 inside those bubbles will then start dissolving into the water. And so this was the first design. It has a lot of holes. There's a lot of holes that were about a the quarter inch entrance is the one back here through this tube. And I'm sorry, the hole entrances all had about a diameter of about 1,500, which is honestly pretty big for a sparger. And I didn't consider how many holes were that many. So when we did do it, it came out like this. We eventually did go to Swery and test the sparger, which again came out like that. The bubbles are they're almost like rupturing. They're very disruptive. And so that doesn't, because they are so big, and because they're being so rupturous, it doesn't lead to very efficient CO2 absorption. And so another problem that we had was all of the air was kind of just exiting through that center and not through any of the other holes. Not enough pressure was building up inside the sparger for it to go and release into the other holes. So, like we concluded, unfortunately it did not go as expected. And as I said before, it all escaped through the center. And so, again, we looked at a brief interview, the holes are just too big and there's just too many. So this is when we came up with the second design, where the holes are extremely small. And they are extremely small. And so we tried 3D printing this. And when we did, the holes kind of just didn't interfere. The plastic, the printer ended up just melting over the holes. And then on top of that, gravity took my sparger and it kind of just broke. So, not that it just broke, but this tube part here kind of just broke off when it fell. And so with that, we came up with just having a fillet. For example, this was the third design, but you can see it did fall and it broke off. We did not want that happening again because people have clumsy hands. And so we decided to add a fillet around this area to make it much stronger and less susceptible to actually breaking. So again, with this sparging process, I did a little bit of further research and to see just what's happening in a way. CO2 is dissolved to make dihydrogen carbonate, otherwise known as carbonic acid. This carbonic acid is a very weak acid, and so to make it a little bit more stable, it releases hydrogen ions, positive hydrogen ions, which decreases the pH level of the water. That is basically what I wanted to see. And then with this picture, I wanted to just show how the sparger makes really small holes, and because the surface area around the bubble grows at a much slower rate than that of which of its volume, the smaller the hole, the more efficient the CO2 can then be absorbed into whatever it's being absorbed to, whether it's the solid absorbent or the liquid absorbent. So then we went on our third design where we decided to find the smallest drill bit that we could and drill it. This is me drilling the holes. We used a little small little paper template right on top of the sparger, and we got this. And I don't know if I want to trust it, but the holes are about a 1/16 of an inch, or 0.0625 thousandths of an inch. And so we just went away. We went away and to just removing all the holes. That way we could just drill. And so for our third test, it worked a little bit better. And the holes the bubbles are just much nicer and look more pleasant. But this weird little, we'll go back, but this weird little moving of bubbles is happening, and we just did not know how to even answer questions having to do with that. So they were going through the path of least resistance. So although the bubbles were nicer, they were only because they were drilled that made it susceptible to human error, which just made it much more likely to have holes that were or less or more different sizes. And so that is why this is happening. Because not all the holes are exactly equal, the air is just traveling through whatever is the biggest bubble, the biggest hole, because it needs less pressure to go through that hole as a bubble. And so, as you can see, it starts traveling here and it jumps quickly over here. So again, even if they were thousandth of an inch off, this would still happen. Any calculations? Just a couple calculations just to understand what's happening. I use Henry's law, and that's basically what is on this paper. Basically, to understand how much CO2 the maximum amount of CO2 that can possibly be absorbed into the water, and found that it was actually extremely small. It is extremely small, and the rate of which the CO2 actually enters into the water, dissolves into the water, is also extremely small. It is extremely inefficient, as we found, to use water and air, just normal air, because mind you, only about 0.0004 moles moles per meter, I believe, is in the air. There isn't a lot of CO2 in the air, at least not enough at this small scale to use air and water. And so it was extremely small, the amount of CO2 each bubble had. And this is assuming spherical cow, where it's supposed to be perfect, even then it's small. I also concluded that assuming perfect conditions, that if we let the sparger go and 100% of the CO2 were to be absorbed, then it would take about 4 minutes for it to reach equilibrium. But with the conditions that we have here, they're not perfect. And so with that sparger that you saw, it would take about more or less 3 or 4 days of the sparger to be active, releasing bubbles, for it to reach equilibrium. in conclusion, the project was enjoyable. It was really fun to research all of that fun stuff. And gave us, me and Caitlin, very powerful insight into chemical engineering. And even though it didn't go as we had hoped, with many design changes and project changes, we ultimately kept trying to apply the engineering design process, going back and redesigning, which made it just more an authentic and meaningful experience. So, any questions?
Did you cross country?
I did do cross.
I recommend.
Oh, really?
I don't know. He like little guy.
I remember.
I got my notes. I think so. Good job. I think the agenda is a little long. Got a lot of words there. Objective is great. Good positive statement. Again, presentation. Those are the main feedback there. I think the way you tested and used the feedback to try to solve the problems, I think that was really good. I mean, that's really what it's all about, right? Like, no matter what you're doing, whether it's chemical or mechanical, being able to assess the data and come up with a solution. I think that's the most important thing. The calcs look good. So one thing on Sparger design, there's like a typical minimum for pressure drop, and that usually helps you avoid those issues that you're seeing, like selectively finding the path of least resistance. And so yeah, so you have a minimum pressure drop typically. It's like a rule of thumb. Yeah, other than that, DAC covers. Good catch on the adding the fillet or whatever you call it, fillet or not a candy guy, but yeah, overall I thought pretty good.
Why did you choose to focus on the Sparger as the main part of this?
It seemed more simple and safer for the most part, and it shows a very important aspect into, at least in the bubble column, as different sizes of bubbles really contribute to how much CO2 gets absorbed into the liquid. And so with the inability to use the amine-based solutions that we wanted to do, or the zeolites, solid absorbent, it just seemed like a good way of showing how bubbles and seeing those calculations really contribute to how much CO2 gets absorbed into the solvent.
Did you end up taking any like pH readings of the water?
We did not take any pH readings of the water, but
Well, would you have been able to detect, I wonder, with the Sparger being the way it was? Could have taken the gas bag. Anyways. It's picky up.
That was fun. I think it's like how a lot to come up with the CO4 and CO2, and you chose an interesting direction.
this doesn't happen often.
This is where you guys stand up and then we do everything.
Morning, Mustangs. This is Mr. Lopez, and I'm still standing. And I'm here with
Chris Blue and Romelia, and it's time for the Pledge of Allegiance. Please stand up. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Now for the Texas Pledge. Honor the Texas flag. I pledge allegiance to thee, Texas, one state, under God, one and indivisible. Now for a moment of silence.
Sing Mustangs, meet me, Keita.
Progress report grades are due today. Don't forget to order your yearbook from Johnsons.com before it sells out. Today is also cap and gown order day in the cafeteria during lunch. Friendly reminder, wear your ID every day and make sure it's visible. This helps us to ensure that everyone on campus is safe and belongs here. Don't forget to close the lesson. Have a great Thanksgiving and see y'all in December.
It's time for the alma mater, real quick. Let's do it.
To sing our alma mater, we sanctify thy name, our cherished hopes and dreams unfold forever as thy fame. We lift our voice, thy praise we sing, thy standards we glorify. We are ever loyal, faithful, and true to thee, our John J. High. As always, have a great day, and go Mustangs!
All right, here we go. Where were we?
Over the questions, comments.
And I understand the limitation of not trying to go with other solvents, so I think this is pretty good for where you went with it.
So I have one more question. What made you pick this project?
This project? Yeah. So, believe it or not, me and Caitlin are like aerospace. Like we want to go to aerospace. And so, the very beginning of this project, before thinking of the Sparger, was us wanting to try to capture the CO2 to do something, you know, silly with that CO2. That was the whole idea. So that's why we had picked this project, but it just didn't seem like we could do that. So we just like moved. We just trying to move into something more. So,
It's a good idea.
Give him a hand. Alright, fired up this low emissions vehicle. Let's go.
Oh, you can see.
Thumbs up when you're ready. Good. All right, gentlemen, go for it.
So, good morning, everyone. My name is Brian Gonzalez.
I'm Timothy Rivers.
And today we'll be presenting our low emission vehicle final project. So, on today's agenda, we have first a quick team introduction of all our team members, as well as the project introduction and what the project is focusing on. Then we'll go into our problem and then solutions we originally thought of, as well as our Gantt chart, key considerations, and then this rolls over to our research on plastic pyrolysis, as well as different plastic types. We're going to showcase our process flow diagram for this process, and then just do a few emission equations and calculations that we did, as well as the final decision on this project, as well as our conclusion. So our team, me and Tim introduced ourselves. We also have 2 additional team members, Dimas Lomos right here and Devin Commerce back there as well. So for our project introduction, as stated, our project was to create a low emission vehicle, specifically just any low emission transport system. So the problem I guess we faced was that it was a very broad term. This could encapsulate cars, buses, planes, trains, ships, even rockets. So what the team decided is that instead of focusing on a certain transport system or vehicle, we decided to focus on the fuel that could run these vehicles. Since all of these vehicles need some way to run, whether it's gasoline, diesel, compressed natural gas, or hydrogen, or anything. So the problem we researched was that emission vehicles account for roughly a quarter of global CO2 emissions. So, which is why the team wanted to focus on the fuel aspects, since if we can make a fuel that is even like 1 or 2% more, or like has a reduction in emissions, that across a large scale, a quarter of the world's emissions would decrease it drastically. So, potential solutions was either plastic-based fuels or hydrogen. For plastic-based fuels, they have a tendency to release less harmful gases, such as like CO2, nitrous oxides, and unburned hydrocarbons, as well as we're recycling plastic waste that would go to a landfill instead. So we can just take that waste and use it to create a fuel that can power the world. And then for hydrogen, it's essentially a zero emission fuel source, since the only emission it produces is steam, which is just water. However, it is super inefficient, and also there's not a lot of modern infrastructure for that. So to convert the world to hydrogen fuel would take many years, also much more cost than plastic-based fuel. So then here's just our little Gantt chart we had. The Gantt chart was important for us to keep us accountable and make sure we're on track to finish the project by the deadline. Also, it allowed us to split our group into 2 sections, so that me and Tim could work on some parts of the project, while Dimas and Devin also work on additional parts, so that we can get everything done in a timely manner.
Okay, so as we said, we're looking at plastic-based fuels. Now, for these fuels, there are a couple of considerations we need to keep in mind. Primarily, the energy consumption of the process. You're heating a plastic, so that takes a lot of energy, as well as the direct and life cycle emissions of this fuel. So for our project, we looked at our specific type of fuel, gasoline versus diesel. There are different pyrolysis processes for each fuel, and they have different energy consumptions. As well as the plastic feed. Plastic feed is incredibly important for these processes, as well as just specifics of the processes, like our type of reactor, and then the overall flow of it as well. So, starting off, just some definitional terms. What is pyrolysis? Well, pyrolysis is the decomposition of plastic into, in our case, into a fuel. We're essentially taking a feed of plastic into this reactor, heating it up to vaporize it, and then condensating it into a liquid form to extract the fuel from it. So, we had a couple options as to what specific fuel we would like to create. We're looking at both gasoline and diesel. Now, these are important to differentiate because they have different chemical structures. When we're breaking down our plastic, it's in this long hydrocarbon chain. And so gasoline and diesel have different lengths of the chains. And so the process of breaking it down is called cracking. So gasoline, since it has shorter chains, requires more cracking, which takes more energy overall. Diesel requires less cracking because it's longer hydrocarbon chains. And there's no sulfur in the fuel as well, which would remove a further refinery process compared to regular diesel. As for the type of plastic we're looking to use, there were a couple different types, 4 main types. This is important because there's a lot of problems that you run into when creating fuel from mixed waste plastics. Our mentor was telling us about a company, I can't remember the name, who had a mixed feed. And when they went to heat up this feed, it solidified into like a concrete substance that jammed the reactors. They had to use explosives to get rid of it. So finding one specific plastic for our feed is really important. So some common types are polyethylene and polypropylene. These are pretty similar. It's when you think of a plastic product, this is what comes to mind. The only difference being polypropylene is a little more resistant to higher temperatures and is food grade as well. Some other types were PVC and polystyrene. PVC is heavy duty, used in PVC pipes, and styrene is used in like styrofoam or packing films. So here's a table our mentor shared with us of the theoretical yields in pyrolysis for some of these plastic types. So we have our polyethylene at the top, PVC, and polypropylene. Now since we're looking for a liquid fuel, we're looking to maximize our liquid percent with minimal char as well. So for polyethylene, we saw at a temperature of 500 and 600 degrees, we had a 52% yield and a 20% yield for liquid. PVC had around a 30% yield, and then polypropylene had both an 80 and a 50% yield at varying temperatures. Now this 80 initially for us was misleading. We saw this 80 and we thought, well, polypropylene is perfect. But what we found is with lower temperatures, the liquid created from this is like a tar. It's a mix between a solid and the liquid we need, and it's unusable. So this 80% is realistically much lower for us. So, looking at this table data, we saw polyethylene did have a high yield, but for actually using it for fuel, it's already in demand for recycled plastics. Most recycled plastic products are made from polyethylene, so it wouldn't be realistic to source polyethylene. PVC had a lower yield, and it releases chlorine gas when it's combusted. This chlorine separates in the pyrolysis process, or the combustion process, and it's extremely harmful to humans. We can't realistically use it for our fuel. Polystyrene is just not economically sustainable to transport. It's 96% air, roughly. So that left us with our polypropylene, which still had a 50% yield at higher temperatures. So I apologize, this may be a little hard to read, small, but this is our process flow diagram. So on the left side here, we have our plastic coming in from the side to prepare it to enter our fluidized bed reactor. This is where we're going to heat the plastic into a gas form that we use later on and refine. But a problem our mentor was telling us is it's extremely difficult to input solids into these highly pressurized containers. So in order to do this, we need our extruder. This will liquefy our plastic to save space and pressurize the chamber so that the difference in pressure will shoot the liquid plastic into the chamber it needs to be in. So once it's in here, it's vaporized into a gas and it creates a solid waste product called char. That's taken to the catalyst regenerator. But the gas is compressed and then taken to the heat exchanger where a cooling liquid condenses the gas vapor from the air, and that's where we get our liquid from. So after the heat exchanger, the gas and the liquid are separated and we have our final diesel product.
Here are just a few graphs about the direct emissions work. So right here would be for CO2 and nitrous oxides in parts per million. Might be hard to read, but diesel would be this black line, so right here and down here. So for regular diesel, it would produces more carbon dioxide emissions than polypropylene plastic fuel. So right here, so all of the polypropylene fuels, even when mixed with diesel, produce lower CO2. So this is like reassuring to know that if we were to like go all in on this, we would automatically have a lower emissions for carbon dioxide, which is one of, if not the main like emissions in the world right now. But right here we can see that nitrous oxides are higher across the board. Now, this there could be many factors to this. However, me and the rest of the team decided that there's like trade-offs essentially. We could reduce the amount of CO2, and then since nitrous oxides are already pretty low, that increase is pretty minuscule even across like a large like sector, across many vehicles as well.
We also found that just using the data, higher temperatures in our reactor does correlate with lower emissions. So the more refined your fuel is, the less of this difference we see.
And then here is just for unburned hydrocarbons. Again, diesel is somewhat better, but however, as we explained trade-offs, perhaps this is like somewhat of a sacrifice to benefit overall emissions. Overall, there's a reduction of emissions, even if some of these are higher. That makes sense. So for emission equations, this is our direct emissions with locality in mind. So locality, what we focus on here is essentially the grid system. So to create this process, we would need energy, and where we get this from the grid. Now, these are values for the ERCOT energy grid that most of Texas uses, which we have values for carbon dioxide, methane, and nitrogen oxide in pounds per megawatt hour. So this is how much emissions, pounds of emissions which would be released for every megawatt hour of energy is used. Now, the reason locality plays a role in this is because if we were to compare like the ERCOT grid system to one in West California, West California has drastically lower carbon dioxide emissions at around 460 pounds per megawatt hour. And the reason is this, because Texas is very heavy on fossil fuels and relies on petroleum, natural gas, and coal for their grid system. However, in other states such as California, they would have more green ways to source their energy, such as wind farms, solar farms, and just more greener ways to get that energy. So this is why locality does play a role in overall decisions. So for our final decision, we ultimately decided that direct emission benefits vary since there is a reduction in CO2, however the increase in that nitrogen oxides and unburned hydrocarbons. So we would have to do further research to see if the trade-offs are viable or not. Also, the life cycle emissions require further testing since we would like to factor in like maybe grids across the nation and compare them and then see if like this is really a viable option for like nationwide use. So for our future steps, if we had like another phase where we wanted to continue this project, we would probably try to test our own polypropylene fuel. So also maybe test different reactor types. So others we did research were fixed bed reactors and rotary kilns. So maybe we can compare and contrast those, see maybe if they produce different yields or have lower emissions. And then we would also potentially like to experience with different feeds. Maybe do like a small scale of the polystyrene, so just to see how efficient that like 4% of actual material would be. And then maybe even market this to companies that could use this diesel. So probably just like large companies that use like many trucks, like potentially Amazon, H-E-B, Walmart, those that just have a lot of vehicles that need to go from places thousands of miles away. So in conclusion, we went over a quick team introduction of our group, as well as introduce our project and then our problem as well that we faced. Then we gave some potential solutions to this, and then showcase our Gantt chart and the key considerations for this project, which ultimately led us to go down the plastic pyrolysis route, researching different plastic types and reactor types, and then showcase our process flow diagram for our fluidized bed reactor, plastic pyrolysis diesel, and then just a few emission calculations and final decision, and then here's our conclusion. And with that, that concludes our presentation, and we would like to open up the floor to any questions.
How did you develop your process flow?
We had to look at what each part of the process does. So the reactor was a big part of it for us. We were looking at mainly a fixed versus a fluidized bed reactor. A lot of the current research we saw used fixed bed reactors, but we saw like if we're heating plastic on a large scale, they're inefficient since the heating comes from the walls of the container. So there's a difference in temperature between the outside versus the inside. We saw with the fluidized bed reactor, we had more universal heating throughout the system, and that was great for energy consumption as well. There's also, later in the process, in the solid and gas separator, liquid gas separator, we're also looking at maybe potentially even using our gas byproduct to burn in either the reactor or catalyst reactor to save energy. I think it was mainly energy consumption that we were looking to prioritize.
So did you complete like overall energy balances on the system, just to say like, here's how much energy we need to put into the process, and how much kind of like, net product you get out per kilowatt or something like that? Did you derive any of those? Did you do any of those calculations?
We planned on it, but with current research, we never really saw energy values for what they were doing. We found the enthalpy of polypropylene pyrolysis. It was around 1,800 joules. I forget the year, 1800. But if we were to continue this in the future, we definitely would be looking at that. That's our main priority.
Did you, and then I guess on the yields, the final product side, did you do mass balances on the system to understand your yields, or did you just go with the research table 50%?
So I think for this one we did with the research table because all of this is relatively like a new I guess technology process so developing, so there's like very like little research, but the research that we did have, we did try to like use it to like as most we could, which is why like a lot of like calculations are pretty much like.
Did you guys explore the total amount of plastics being generated in kind of a Maxwell's question, like how much plastics are out there to convert to fuel, and what does it do to the amount of fuel used? Like just looking at those two numbers in terms. Basically, I'm just asking like if you have X amount of plastic, total plastic, if you convert all to fuel, what does that do? How much fuel do you make for the consumption that you're trying to replace, right? So, I don't know, to me that's an interesting question. Can you make enough fuel to supply that amount of diesel that you're trying to replace?
Off the top of my head, we hadn't looked into that, but there have been companies that have tried this, and there are companies that are actively trying to connect plastic suppliers and those who are doing this. And so we figured if they are able to have a business in this, it would be sustainable. As for the specifics of it,
And I think it's more about not like fully replacing diesel, but like having it like backup, I guess, because these process would be to get like essentially recycle this polypropylene plastic into something that's more usable instead of just like throwing it away.
Yeah, and
Do you guys have any, in terms of like the economics of these like processes, did you guys look into anything about just sorting plastic? Because one big cost with doing any kind of like plastic recycling is the sorting of the plastic. Because the plastics are collected in bulk, and so you have to pull out your PVCs, you have to pull out your polyethylenes to get the plastic out. So did you guys look into that at all? Or kind of see what that would look like?
For like the economics aspects, we did talk to our mentor about it, but we ultimately decided to skim over it. But the plastic source that we just settled on was Allied Plastic Supplies, located here in Texas, and I think they're like mostly have like just polypropylene source. So I think that like should get this like reduce the cost of like sorting since they have like that like specific plastic.
Can you describe like a challenge in this process that you guys faced, or like that you struggled to understand or had to work at, and maybe how you approached solving that problem?
I would think the project's topic in general, pyrolysis, just because there's so many logistical concerns with this. There's so many articles, research articles, describing why this process isn't viable. And so finding a way to somehow make this work logistically, like having to worry about like our reactor type and plastic type, going into this project, we didn't think we would have to consider that. We thought we would find a process, and that would be easy, and then we would focus the project timeline on calculations and maybe coming up with a plan for marketing this to companies. But realistically, what we saw is it was primarily research and figuring out, well, logistically, how do they make this work, and how does this work in real life?
Yeah, I thought it was great. I think your intent was clear, your purpose was clear, the definitions. Y'all were speaking about the subject like you're experts in that. That's a good skill to have. Yeah, I thought that was great. And then choosing fuel, the way you showed it, that we can have a big impact because we're going to hit fuel. And then you got into the presentation. It's like, well, there's some pluses and minuses. I think we see that all the time with any type of technology. So that's great. Great experience for y'all and great background information. Communication was great. Presentation was great. Appreciate y'all dressing up a little bit. That's good. And again, the research, you did great research on the forming and the usable calculation for you. yeah, I get what these guys are asking about the background and understanding where that's kind of where we usually start. Just very fundamental, you know, enthalpies and energies in and out. But there is a lot of data out there, and it looked like you had some good references for that. Yeah, and ultimately, yeah, I thought that it was cool to see, you know, this is a great idea, and it does reduce CO2, but by the way, it also reduces regular diesel produces less NOx, and there's other things to consider. This is the challenge that everybody is facing in that area. So that's good. Yeah, and I was trying to get at, like, why did you pick plastics as the resource? Like, what, from your point of view, you know, why was that?
We had seen this person on the internet who had figured out how to do it in his backyard, and he's promoting it online. This is the fuel of the future. Why isn't everyone doing this? So we were thinking, well, why aren't people doing this? we thought it would be a good presentation.
That's great. And I noticed a lot of emphasis on CO2 stuff. Like, for your generation, you know, do you think CO2 is a problem? It's something that you think we'll be trying to address?
Absolutely. One thing we did learn from this project is that it's not just CO2. There's also sulfur and nitric oxide, which we are emphasizing as much as we can.
That's right. Cool. Yeah, and everybody forgets methane. Methane's also a
Also, yeah, hydrocarbons.
Oh, that's the good thing. It goes pretty fast.
What? Oh, methane doesn't last as long.
Yeah, but it's 4 times work.
But anyway, good, yeah, good.
Give him a hand. So while the mentors are finishing their scoring and the rubric, we started late, but guess what? We got off. We're right on schedule. For the mentors' benefit and for mine too, we're gonna have a intermission, so we can go to the restroom or stretch your legs, and then batter up is gonna be the agricultural rover. So we can actually bring it up here and we can start getting ready for it when we come back. Great job so far, guys.
Thank y'all for being here. Thank y'all.
It's our principal, Ms. Ware. And then there's,
So there's a guy that recruited me over for yes. I always was over that. And I used to know that. So I found his and he was great. Also, he started out, he wasn't as great. From scratch.
And then go back.
Actually got some of those players where I say to both finished it and he would
Oh, for sure.
so yeah.
Of course.
Yeah.
I might be back later.
Okay.
So I tried to.
You guys need to go to the restroom.
Be right back. I do have to take a break.
I mean, I wasn't dating for 3 years. Yeah, it did functional. It's a little guy. It needs a name on the tree. I don't know if it's a tree that fell. Like, I don't know, server got fixed. Power line.
No, not one like that. I don't think Like, I was like, I don't remember how now, but I just remember they did make it up. So let me see if I can and so at the time my oldest was like, all together. So my cousin and so everybody's been arguing okay, so because then I sent it to my husband and he's like sending it to everybody he knows and he's like bragging about like, oh my god, like this is so amazing. Because he actually taught my 3-year-old. I was like, no. He did the water, okay? He didn't do like the
Is that also something you guys are really interested in?
Yeah.
I'm like, okay, I'm gonna show it to you. You're like,
Well, I'm
he was like, hug. I was like, you said
I
climate.
could
I said,
find
we did it.
Well, I tried. I mean, you can get Mickey's ball, but you can get these.
I just want, do you want to control this or do you want to use think about that. It's fine if we continue, I'm fine to continue the version process as well. But if you want to think about it.
I just feel like this project, when we first had it, it's a really good idea, and I feel like it could help a lot of people if we were actually going to get it out there. But for you for the robot makers are really cool. So.
Well, keep us well.
That's true. Take
Right now, you guys, I mean, I really familiar with the original. So to me, it's like, if you continue with that, I can give you guys. You guys are self-motivated. With the other project, it seems like it's.
He's not a 3-year-old. I'm like,
Maybe that's more what you
he
guys.
did the water, okay? He helped me like calm down.
It's not my business. Well, don't do that. You're a seniors, you're about to go to your last semester, you're gonna think that, oh, I wanna do this, and then you're gonna think, you're actually wait. So, senioritis is real.
I was like, I'm gonna come.
It's coming.
Pictures and be prepared to not
It's coming.
understand.
It is coming.
Oh, some I'm like, no, 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 no. You can't be rusty yet. You still have one more grading, you know.
This is how principals
I
work.
already know.
Academy.
Thank God for being here today.
And capture macro, and calculus, and reading.
So you're my life.
I have very twin twins. I'm online to like, but I already tried to I'm very.
So that's, I feel like it's starting off just to 20 decisions.
Because she's thinking also, like, I'm probably not going to get into all of those.
I got the Just like getting them letters.
I'm like, if you don't, then who will, okay?
My
So,
mom said we could put them all in like a spin wheel and then like spin it and like whichever one it wins.
That'll be a big decision matrix.
The thing about it is, don't do it all the time when you can only work
right. That's it, yeah. Where do you feel like this is your vibe? And they need to show you the money too, like honestly. Like, you're too good for them not to.
Probably like the worst.
Yeah. Show me the numbers.
Some of these schools it's like $60,000 tuition each semester.
You said you're looking up in the Midwest.
Yeah, like the North.
Purdue.
Yeah, Purdue, Rochester University, Cornell,
Carnegie is tough.
Yeah,
West Lafayette, my fiance actually.
Oh, yeah.
That's very cool, very good name.
Stop studying a lot.
Do you want to be in Chicago?
Really? I see you as a Chicago person. I would say. Have you been to Chicago?
Or if you're looking for that far, you like
I visited Chicago and my mom and I kept driving the wrong way down freeways.
No, you don't drive though.
Well,
No, you don't drive there.
That's the fun part of the trip.
No.
I'm walking in.
Yes. Yeah, you wouldn't drive. Like,
We ended up in a situation where we were going the wrong way and there was a train.
No!
And everyone was screaming and I was along the street.
Yeah. That's like driving in. It's like, here's what it is. Have you heard anything else? Yeah.
So, yeah.
Should I tell you? Yeah, so that we're UT people, but so it makes sense all and it's true. I was like, let me tell you something. If David gives you a full ride, we will get them all. Okay, I don't hear nothing about like whatever. We are not UT-ish right now.
We have actually like ones that are both higher and
Yeah, that's true. And Jeter.
Jeter went to UC.
That's true.
Dyer
That's
went
true.
to
Yep. House of Knights.
So that's an interesting one.
Yeah.
I don't know. You guys wanna do one so you can get to back Okay, guys, we're gonna continue so our mentors can go back to work because they are busy people. I don't know. You agree with me on that? But, Eloy wants to go back to work. All right. So the next presentation is agricultural rover. Ready? Late. Turn off the rover. Whenever you're ready, sir.
Hello, I am Nathan Longoria, and together with Kyle Kishner, who's over there.
Hello.
We are part of the agricultural rover. We are doing the agricultural rover project. Today we will be going over the project details, the solution we came up with, the construction process, the problems we've encountered doing so, the control scheme for controlling the rover itself. I'll then be showcasing the rover, and then I'll go over future plans. We were tasked by Mr. DuPont to make a rover that would help cut back on like water that's wasted when watering fields. So normally what they have for agriculture nowadays is either some sort of in-ground irrigation system that just waters everything the same, or these large like giant structures that rotate around a single point that water the field, which causes some plants to be overwatered or underwatered because the coverage is equal, but each plant does not always get the same amount, because a plant can cover another, or it could just be in a spot that's secluded away from the irrigation. We plan to solve that by making a small rover that could move up and down like the rows of the field itself and detect the moisture around each crop individually and water it accordingly to help cut down on help cut down on water waste, because water is important. And yeah. So right now for the prototype, we have made a rover that can be driven around, have the sensor that can be moved and buried into the ground, and then take the moisture level of it, and then allow for releasing water onto the crop. Here's the rover. Basically, this is a basic SolidWorks model of the base itself. Here's one of the pictures we took later on as it was being built. We made it out of these Tetrix parts as a prototype to just have like a proof of concept and make sure everything, like the code and the idea behind it works. So, and since we have over at the robotics shop, we have like a lot of these parts, it was a very good way to help cut down on like any cost we might take while building this, because most of the parts we could get just from the robotics shop itself. Notice how up here there's a giant space right here, and all the electronics are focused here. That's because right here would be where the water tank would be positioned. With only like the barest minimums of like electronics, like the motor sort of back wheels and the pump itself. And that's to make sure that all the electronics stay away from the water where it's held, to basically make sure that nothing bad happens, like a small leak doesn't get on everything and just ruin the entire thing. The arm mechanisms. Right here is the main arm part. This is the motor axle that attaches to the motor, and inside this channel there's a small pinion gear that drives the rack to allow for it to extend outward and back inward. Then here on the sensor part, there is a servo attached to this gear, attached to this gear in a 4-to-1, I believe a 4-to-1 or stuff, a 1-to-4 shift to drive this pinion gear that powers this, that moves this rack right here. This here is the moisture sensor we are using. It is a capacitive moisture sensor. And there's two different types. There's a capacitive moisture sensor and a resistive moisture sensor. The resistive moisture sensors work off of having two prongs that send an electrical signal back and forth between them to detect the resistance in the soil itself, and use that to find the moisture content. But they are they're less reliable than the capacitive moisture sensors, which work on basically putting a charge into the soil itself and seeing how well it holds the charge. So, and they're way more reliable, and Mr. DuPont told us to use these, so that's what we went along with using. Then we come to the problems we faced while working on this. During the second week, we had a kind of a lull in just like overall production of the rover and such, because there was like little communication between me and Kyle, and we were just like not focused on the project itself. But we were able to quickly fix that and like really quickly get right back on pace with what we were supposed to be. And then on week 7, we had eventually started building the robot itself, but we came through a problem of we weren't able to test any of the main electronic mechanisms because we didn't have a 12-volt battery that worked. Because most of the ones in the robotics shop were burned out, or just unable to hold the charge. Thankfully, we were eventually able to find this one, which does work. So, and we were able to get that fixed really quick. During the entire process, we had many problems with the code itself due to the Tetrix teleop, which is this part right here that is meant to connect the controller to the Arduino itself. Is meant specifically to work with the Tetrix Prism, which is the specific controller that Tetrix pieces have. But as we need a bunch of different smaller ports for all the stuff we were doing from we used an Arduino Uno, and a lot of the problems came from trying to connect the teleop to the Arduino itself, because most people don't usually go about connecting the teleop to the Arduino itself. They just use the Prism because they usually have stuff that already interacts with the Prism itself. And then there's trouble getting the stop function for it. Now, what do I mean by stop? It's basically because not what like an actual stop function like in code, but it's more like this variable we had set up so that when the arm is extended or anything, the wheels don't move, so that you don't have the sensor buried in the ground and you aren't able to just start driving it and break the sensor. We made sure it's basically a variable that turns on when this is no longer right in this position, so that it makes sure that the sensor is all the way retracted before you're able to start moving again. But we were eventually able to get that working. Then there's the steering problem. It was mainly caused when just trying to steer it by itself without driving it forwards or backwards. That's because the left side is wired up to are wired up together, and the right side are wired up together, so that when the left side always has the front motor and back motor on the left side always has the same power and direction, and same with the right side. So when trying to get it to rotate like standing still, we had first made it to where the wheels on the left side go forward and the wheels on the right side go back, or whichever direction they're trying to rotate it in. And that caused to where there was a point of rotation here and a point of rotation here, which was causing it to basically try to tear itself apart. We fixed that by just making it to not be able to be turned while without going forward or backward. A very simple solution, but it's mainly just to get the prototype working. Because we were going to completely redesign like the steering system when in our final product. And then you may notice there's no water tank. That's because when we initially started this project, we were doing all of our time for a deadline. We were scheduling all our time around our deadline being sometime in December, but for like our presentation for the prototype. But 2 weeks ago, Mr. Rivera had told us that we would be doing it this week for Thanksgiving, so we were we were getting the prototype up and running and weren't able to do anything to get like a proper water tank or test like the water dispersal ability. So with that being said, we are still on track for like our goals. You can see it better as if you can read it. It says down here that down here is writing final presentation and presenting the final presentation, and they're marked for the 18th of December. And we are still technically on track for that thing to get the water tank not only fully finished but also start getting testing and stuff. Then the controls, R2 is very beautiful. So first, the left stick, moving it forward makes the rover move forward, and moving it backward makes the rover move backwards. The right stick basically allows for turning, and then the R2 button, when held down, stops all movement in the motors and allows you to do all the extra functions like moving out the sensor and doing the moisture detecting the moisture level and spraying water. The D-pad controls directionally, so the left and right move the arm in and out, and up and down moves the sensor up and down. When the sensor is not fully up, you can't move the arm left or right to once again help with making sure the sensor stays safe. Then pressing the square button will start detecting, will take whatever value is from that the sensor is giving out and then display it on the LED that's on the controller itself. If it's green, then it's within then it's in good region. It's within a good amount of moisture. If it's red, then it's below whatever set amount of moisture that the crop needs. And then holding down the circle would start up the pump to spray water. That's not it's just a little bit. I guess we're now going to learn what is going wrong with the robot, with the rover. I guess this multimeter is dead.
I'm sorry. Hey, you all know technology.
Never do it live though.
This is all part of the plan. This is exactly what I was hoping to happen. Yeah.
With a good attitude.
Black wire's got in there, right?
Yeah.
Should take off on.
working
should
during
have
this time.
tested this in the morning when I got here.
Yeah.
It was working just fine, now it wasn't.
Yeah.
Maybe the LEDs just like all died on every single thing, and it is kind of on power. Oh, that's why. Kyle, can you go grab the box and bring it to me real quick?
Alright.
Yeah. You guys will get to see the rubber. Just give me a second to do an impromptu trick. Careful.
All right. We have plenty of time.
Was it for
Just gotta do a little repair.
Smart. Are you greedy? Get money? No. So 1,990.
Yeah, they started this thing from scratch. I mean, the pieces were just like blocks. They kept
Yeah.
this issue. Robots.
It was like,
It's probably like right around.
Yeah, we
funny
used to do it.
because-
The Ohio State still does a first year.
We don't usually play games.
Engineering
It's like
competition.
actually-
You have to have like a set of tasks that it has to do, and it's for
And then so
time.
that.
Yeah.
And students are standing up past midnight trying to shave seconds off their time. And then they show up on competition day and it just doesn't work.
That's why competitions usually have time factoring for discounts.
This is
But it takes us a little while to move
points
it.
are different.
Yeah.
That's what it is. I don't know like what happened there.
No.
Like, Jordan got
No rush. You gotta
What did you vote to? Really?
Yeah. Right. Well, I see lights.
Don't do this. Don't just like shove the wires together and take them off while it's on. Don't ever do what I do.
Oh, no.
Yeah.
Floor, yeah. Yeah.
Watch your feet.
Yes, it works.
Yay!
The way out damage is caused by it does in fact drive.
And if you extend the arm, you can't move.
Yeah. Let me get it to a point where like everyone can see it.
Oh, right here.
Yeah.
Yeah. Robotics.
Where is the arm on it right now?
Yeah. Oh yeah. It's just finding a spot.
You'll notice it sometimes flickers. That's because the button that detects whether the arm is fully retracted keeps disconnecting for like milliseconds, and that's what's shown on this light. If this light's on, the arm is fully retracted, and that disconnect, that like small thing makes it like flicker and locks up the wheels instantly. So as soon as the arm comes disconnected, even if R2 is not held down, the wheels stop entirely.
Can you demonstrate the arm going down, or is it gonna break in with it?
Yeah, I'm gonna just put it up here so that the arm, it doesn't like try to bury into the thing. And it's way easier to see when it's on the table. No, just to see if it like go down. I guess it moves, then it goes down.
And you guys haven't gotten the box in here yet.
Yeah. And see, since the arm is out, I can't drive it around. And I can't even move the arm sideways because the sensor is down.
Yeah.
So as soon as I raise it up,
Right.
fully, then I can bring it back. Then square makes, since it's not in soil right now, it's just going to give a green. So you can see it does the back work, and the pump is very silent, but I'm just going to bring it around. Because even when you touch it, you can feel like turn on and vibrate. There's still, it's one of the small ones you see at the bottom of like there's a capped water fountain.
I was in here 3 weeks ago and I was just like drawing it. It's like, what? That's crazy.
So far.
So far.
That's so cool. So they have, you're going to have a longer tank? So that's
For future, we're going to rework the steering so that's like way better handling. You can see as I was driving around, I had to multiple times like back up and such to get it to turn in tight ways. Then we're gonna finish up the storage unit for the water itself so that we can hopefully like actually test like watering and such. And then we're gonna make it autonomously controlled so that you just like set it down and it will be able to find its way into like a row and just do it without you having to intervene or anything. So, and then make it like an actual final product that should be hopefully like way more waterproof than this is with all the wires hanging out and stuff. Any questions?
What is the intended like in the grand scheme of things? Like, how big would this really be?
It's currently 16 inches like this way, which is wide enough to fit in. It's small enough to fit in some crop rows because they range from like 1 to like 3 feet. But like there's some that are like 1 foot, so long, so like wide. So hopefully we're going to decrease it this way to make sure it can fit within those like narrower rows. Then hopefully if we can make it like shorter this way, but since they're like rows, the length doesn't really matter that much. And
much water is dispensed when you use the pump?
We have not tested that yet.
Because the thought in my head is how often does it have to go back and refill on water?
Yeah.
Which is just something to consider for the future.
We will.
So when you're, for your next iteration of steering, are you planning on still using alternating wheels, or are you gonna actually go to like a rack and pinion system?
Probably some sort of rack and pinion system because it allows for way tighter turn circles. And with because we can make that driven by a servo, so that we have more finer control over the steering angle, and I would hope with autonomously doing it rather than just doing a whole lot of just kinematics equations inside like the Arduino code itself, just to make sure it's turning 90 degrees.
When you were doing any research, did you come across any of this? Like, are people doing this right now?
Not that I've looked, but most of the time we haven't really looked into if people are doing just more just how to. We were more just looking into how like the sensor itself would work and how we might be able to just make this.
That's awesome.
Yeah, I'd say I really like the focus and your troubleshooting aspects. I mean, we've all gone through that, and to see it like lined out and how you solve the challenges is really great.
How much did your design help you with the fab? Like, was it easier to fab because you had like, I don't know if you had like a detailed design.
It was very helpful to design because as you saw in like the previous slides, we made a full like model in SolidWorks of like the base itself, along with the arm and the sensor, the main arm and the servo part of it. We made it all in SolidWorks, including the screws and the nuts and everything. Not only to have a way where we could just move stuff around without having to like completely unscrew a part and recreate it, but also be able to collect, to know just how much parts we need to get from the robotic shop, so that we know just how much stuff we're using so that we don't like get too little and have to constantly go back to get like more and more parts.
So you had a good bill of materials of what you needed. Everything you needed.
Yes.
Good.
That's good. Yeah.
Give him a hand. Hi, good job there. I'm impressed with your troubleshooting techniques. Outstanding. All right, next theme is hydrogen cell.
So I'm Victoria Afsani.
You guys good?
You ready? Oh, you're ready? Oh, hold on.
Anytime?
Sorry,
We got plenty of time. Wait a second. Yeah, just 1 second.
Okay.
That's perfect.
I got a great story to go with it too.
I mean, that's all you need. You just need a battery with like at least 1.6 volts, and you can support water. So perfect.
The
binder close.
I just like brought a pencil and
That's perfect.
Yeah.
thumbs up when you guys are ready. We're good? Good. Go ahead.
I'm Victoria Khan.
I'm Maurice, and this is our hydrogen research presentation. This is our agenda. We'll go over our project overview, our main problem, model design, regulation, Python modeling, and our conclusion. This is our introduction. Hydrogen has the possibility to be a clean energy source. It could be used to power vehicles, buildings, and even used as fuel for rockets. The way we would produce hydrogen is using electrolysis. We would split water into two gases using like an anode and a cathode, and it would split into hydrogen and oxygen. Depending on the application, the materials to split them would either be platinum or noble metals such as platinum or iridium and other carbon-based materials. Our main problem is that hydrogen itself needs a lot of power to be produced, and the energy that with battery electric vehicles, they conserve at least 80% of their energy, rather than hydrogen, which conserves at least 20 to 25% of their energy. Also, the source of hydrogen comes from steam methane reforming, where it takes some sort of gas, natural gas like methane, and mix it with steam and a catalyst, and it will produce hydrogen. And right now, 90% of hydrogen production is made from steam methane. And the cost of it is way lower than electrolysis, usually $1 to $2, and electrolysis is like $5 to $6. And this is our Gantt chart. This is what we use to plan out the entire project throughout the few months that we had. And then we had two solutions for our project. One was an alkaline-based electrolysis, and another one was PEME, or proton exchange membrane. There was another one called solid oxide exchange, I believe, which we scrapped because it required a lot.
It required a lot of dangerous gases, and we just said that we did not want to put that into the air, and so we scrapped that idea completely.
The main difference between the two, alkaline and PEM, is that alkaline is lower cost, and PEM is much, higher efficiency, purity, and a more compact design. The cons of PEM, though, it's really expensive due to the materials like platinum. It's really hard to find. And the cons of alkaline is that it erodes quickly, lower gas purity, and has a lower energy efficiency. And this is our demonstration.
So this is basically what alkaline is doing. So I was just able to steal these from the chemistry lab. And so we have our positive energy going through here into our anode. These are this is graphite. I stripped from a pencil. I broke a couple, but I was able to get it out. And inside this is sodium hydroxide. So you don't want to touch that, it's highly corrosive, but it's a very strong alkaline solution to make this, to put more hydrogen and oxygen into the water and make more hydrogen and oxygen product. So, yeah. Oh my god. Are you telling me the yay! Low light. That's nice. So, fun story about this actually, I left this on because hydrogen and oxygen bubbled at the cathode and the catalyst. And so then you get to play this really fun game of what's that smell in a chemistry lab. And then you get to play another game called Is This OSHA Approved? And it was. So it wasn't dangerous. it just created ozone, so that's what happens when you use a janky setup like this. The graphite is pretty rough, and so because current concentrates on those rough edges, it splits the oxygen once more to create O3 instead of O2. So I'm gonna take this off so we don't have to that again.
And after coming up with a solution, we made a design on the type of cell. We just had to go with 10 because it was more aligned with our problems, since we needed a higher efficiency and less power consumption. So we looked all over the web and we found Senza, a company where it makes hydrogen cells, and we used that design and other designs and create our own. And this is our solid model. We decided that we would design after we, drawn a design, and that's our 3D printed parts. We had a base model with just a simple what's it called? Anodes and separators, gas. Yeah. And we had a defined model later on throughout the week. This is our printed dummy model, and you can see the end plate, anode collector, cover gasket, separator plate, and a membrane. That was after we completed our model. And then this is our photo.
So now that we have our basic components of the cell, this is essentially what is in every single PME cell that you make. So at the start, you have your compression plate. It's basically like a sandwich, basically like the bread of your sandwich. So you're gonna have this mirror on either side and it holds everything together. It's very important to ensure contact between all of these layers, so the electrons don't have to jump between, and then you introduce loss. So here's our bipolar plate. It's kind of cheese. I like cheese. It's where our energy is introduced to the system. Then we have our silicone seal. I don't really have a good sandwich metaphor for this, but basically it keeps everything insulated. You don't really want this getting too hot, and it keeps all of our water from leaking. That's a big problem. So inside the silicone seal is our porous transport layer, kind of like lettuce. You're gonna have multiple meshes stacked upon each other in order to increase surface area. So this is what's gonna oxidize the water. So where energy meets water, and that's where it's introduced into reaction. And so here's that ME. This is kind of where I got my inspiration for the sandwich, because I was hungry and I saw a T right there. And so I thought, hey, this is the meat. This is where all the stuff happens. So here's our gas diffusion layer. It keeps all the water separated from the proton exchange membrane and the catalyst. So here's our catalyst. The main part of the catalyst is to lower the activation energy. And so one problem I had during this process is figuring out, okay, well, here's the gas diffusion layer, here's the catalyst. The water doesn't need the catalyst, so how is this reaction even happening? So on the microscopic level, electrons don't see anything at all. They only see the catalyst that they really want to go to. And so they basically just leave their really tight bond with water to go to this catalyst for a hot second and then pop off again and release into the system. And so from that, because hydrogen is now free from its electrons, it can pass through the proton exchange membrane and then go all the way around again to the other side of the sandwich. From this, our water goes through here, the inlets. Then you have your products at the catalyst layer. So that's our water with O2. It goes around through flow inlets while the hydrogen goes through a different route. And then you can have pure hydrogen on one side, a mix on the other side. And so we can't really create this in a classroom. We don't have the materials, and Spheri is still getting them for us. And so how are we gonna analyze efficiency if we can actually make a cell? So I use literature review, it's just those equations that identify trends between losses of energy. Mathematical modeling for the PME cell with Python, so we're applying that math that we got from our courses. And then we have cross analysis to compare and validate between all our sources. So this is our equation simplified. Our V cell is the total energy of the system, plus the spherical Cal's minimum, plus the activation energy, plus the Ohm's law, plus our mass transport. So I'm going to get into all of these, but this is our application. So Gibbs free energy law, this is something we all learned in chemistry 1, or at least you should have if you remember right. You take the change in heat, you take the change in temperature, in entropy, and LP. Sorry, I looked dyslexic. And then you can apply that to your energy rev. And basically our minimum from this really long equation is 1.29 volts. This is our spherical Cal's minimum for any of this to happen. So activation over potential is to sort of kickstart the reaction. The last one was the spherical Cal's version. This is how much you actually need in the real world. And it's also the speed of charge transfer at the electrode and electrolyte interface, or where the conductor and the ion conductor meet. And so this is where our exchange of current happens, and we can get that with the Buserow-Volmer equation. As far as I'm concerned, you share a name, you're married, so that's why they have a little heart. And then I learned in actually my physics C class that you can apply this and get slopes from these change in voltage and change in currents. And this slope is going to be our constant in the activation energy equation. So we actually can't make this because it requires experimental data with the Buserow-Volmer equation, but you can get estimates based on just what's sort of standard. So temperature, Faraday's constant, number of electrons, gas constants, and things like that. So Ohm's losses, pretty standard. It's an obvious loss in the system. You take all the resistors plus your current that's going through it, and then you get your voltage. So we're gonna add all these up. It's the thickness of that particular component times over its conductivity. And everything on this side needs to be doubled because it's the other half of the damage. So mass transport losses, this is kind of complicated. Basically, if anything happens that you don't really know what it is, it's probably a mass transport loss. So what happens is, because you're feeding all of this into the cell, hydrogen gets to go out and go on its merry way, and then you have oxygen bubbling around the anode side, blocking hydrogen from going through. And so oxygen has 3 layers to get out, and the best way to think of this is kind of like a maze, because on the microscopic level, they don't really see blockages, they just see hallways between the fibers of the gas diffusion layer and the core stage transport layer. So our thickness is how long the maze is, our porosity is how wide the maze is, our torosity is basically how twisted the maze is. So you can kind of imagine as people are going in and out of this maze, these components basically define how clogged up is it going to get. And so this is a really important thing when you're doing experimental data and applying it, because you don't want to reach that point where the maze is so clogged that you're reaching basically towards infinity voltage and not getting anything out of it, because oxygen has completely covered the catalyst. Okay, so this is just a snapshot of all my code. The source code is from Copilot and ChatGPT, because every time I write something, it tells me I'm wrong in 20 different ways. So I took, what's it called? An outline from Copilot and ChatGPT, and then I have to go in and debug every single function, because you can't really rely on AI to do complicated equations like this. And so this is why it's really important that you understand what you're talking about and how all of these equations fit together, so you can actually make an accurate model. So here are my modeling results. Our activation, if you remember that log, kind of looks like a log function, right? This adds 0.35 to our system of minimum energy, so that's our 1.29 plus 3.5, and then our Ohm's law is basically constant, so that's 0.46 based on the materials I used. This whole base thing is just on like a standard PME cell. You used a platinum catalyst, you used titanium PTL, you used carbon mesh GDL, things like that. And so this just depicts the relationship between current density and the cell voltage and where all the losses are as our hydrogen production. Pretty basic, based on Faraday's law. You take our current and the activation area over Faraday's constant and the number of electrons too. And so from this, again, it would cap out at 3.35 because that's our J limit. And on an hourly rate, this would be 20 liters per hour. But based on all these cells, we usually get 50% yield. So that's more like this. And if we go back to our inspiration for this model, the percents up, they have very similar numbers actually. So that's 9 liters per hour compared to 10, and that's 3.5 voltage, and our limit was around 3.3. They're probably going to want to go as much as possible in the industry, so the cell can erode faster and we buy more, right? And just to maximize the number of hydrogen energy we can get out of the cell. So our cross analysis validation, this is really the bulk of what I was doing. Of now that I have like a semi-accurate model, where are all my losses and where can I cut costs? So I looked at other efficiency models from my sources. And so let's start with the similarities so I can build some more confidence. I have 1.2 as my minimum. This is pretty good. For activation losses, they all kind of cap out around 1.6 between 1.8, pretty similar. But then we are talking about Ohm's membrane over here, and they look pretty small, and they also don't have GDL over here for some reason. Versus mine is almost double the energy cell. So what's going on with that? And I need to go in and impute more data. So from this, I just played around with my model, and I found that the only thing that was really stopping efficiency was the PME stuff, the PME membrane itself. In hindsight, protons are 18,000 times heavier than electrons, or 1,800 times heavier. And Nafion is designed to reject electrons to present a short circuit between each end of the anode and cathode. And so going in and looking at the raw values, you can see that our membrane versus our R total is really the bulk, and none of these really matter in the grand scheme of things. And so when I put that back in and I used ideal Nafion, so instead of using like a paper cardstock, I used something like as thin as this hair. That's what you use in very high level research. I got something that was very close to one of my sources again. Yeah. So this is our main energy loss in the cell that I was able to change because of the activation energy. I can only change that without experimental data. And so then I looked at the cost across all of these cells. Our premium cells are going to be 4 to 7K, 800 to 1.5 is like just the industry standard, what I've used. And then our low cost cell is what I'm trying to get to. So I'm looking for something in the middle of this where we use a pretty good PME cell, PME membrane for efficiency, and then all the other costs we can cut because they don't really matter in the grand scheme of things. So yeah. And then my key findings, again, homocysteines are mainly delivering with the hardware. The mass transport limits occurred more than expected. This is just based on my literature review and things like that. Everyone had varying states of data. Again, this is our mass transport loss is the thing that it kind of just happens to happen, and if you don't have an explanation, it's probably that. And then after our own losses, activation was the number one, so we should probably put more thought and effort into this. Ooh, I'm talking a lot. Excuse me. For research, what did I personally get out of this? I remembered something. I'll come back to it. So, as we're going through this process, all of my research papers were probably like within the last decade, and in the middle of the process, like October 22nd, and I've been at this for like about a month, Rice University just drops a new catalyst that's apparently super efficient and super amazing. So now I have to take this into consideration too. But point is that the field is innovating every single day, and that even though we don't have the technology now to cut back on losses for the membrane and the activation, one day we will, because we're getting through there every single day. And then the real kick that I got out of this is that the research papers use a lot of good words. I know I use a lot of good words for presentation. I try to cut back on that as much as possible. But I'm really proud of myself, because at the start of this, I was just like Egyptian hieroglyphics, right? And then now I'm able to look at these papers and sort of glean 80% of what they're saying. So my recommendations is we want to prioritize membrane quality and catalyst optimization, not PTLs. We need to expand testings on these. We need to look into the study of bubble management, because it's very, very mystical. We don't really know what's happening. Just sort of everything that's wrong, we'll chuck it into that category. And then we need to push our research more to cost per H2 and not just efficiency, because then more people are going to be willing to buy this if it's not going to cost an arm and a leg. So why this matters, I'm trying to make green energy more accessible by reducing cost. This challenges the assumption that expensive materials are really needed for good cells. The only expensive materials that you need are the PME and the catalyst. Everything else would be cut 30% of the costs on. I want to normalize hydrogen by proving that it's simple and scalable. I don't know how well I did that, but maybe with my sandwich analogy, you sort of got the gist of it, as compared to like a windmill. It's very intuitive that you have something that moves next to a generator. So for my next steps, hopefully we get materials from Squiri soon, and I can actually make a cell and refine my model from it. And then expand, include other variables. That's a big thing in all of these other research papers. How does the temperature affect it? How does the resistivity affect it? How does anything else affect it? And then I want to optimize design for cost and efficiency, and hopefully make this into something I can post online to make hydrogen more not so a scary thing. And that's our presentation. Please ask questions. Yes. Okay.
What do you want to be when you grow up?
That's a great question. I want to be an aerospace engineer with a systems degree. Like halfway through this project is when I realized, oh, hydrogen can be used for rocket fuel. And I actually found out that NASA is making PME cells similar to this, like on the moon, like with their Artemis missions, so that they can be able to make hydrogen rocket fuel just on the go.
That's awesome. Yeah, I mean, I would say you could be a chemist, chemical engineer, you do whatever you want.
I have very strong fond memories of my chemistry class.
Yeah. I mean, you definitely want to go engineer, not chemist.
Miles.
Oh, Miles. Your response. He's a chemist, though. But, yeah, so this is awesome. So I spent like 2 years, probably 20 years ago, we were working on chlor-alkali, and that was our whole goal, was to get as close as we could to that E0. So all that stuff we talked about was very, very relevant. And we tested temperature, we created microchannels on the surface of the electrode. We tried to deal with the bubbles like you're talking about. We used coatings instead of just platinum electrodes. We used coatings on that. We used nickel coatings on that. We used niobium.
Yeah, the one branch structure was iridium and rhodium like ratio, and I think they were going to get that down to like $20 a gram. That's way in the future, obviously, because they just published that paper. They probably spent thousands of dollars making this synthesized catalyst. But again, in the future, as these research papers come out and costs go down, then this could be a very good energy source.
That's really cool. All I had back then was books and an okay internet. Now, now you have time and resources. So, yeah. But I think both y'all did a great job. The background was really good. Awesome that you're using Python. Everybody's making Python models nowadays, so really good. I thought it was very ambitious to try to design your own electrode, and of course you got to be careful, right? You're using that as an example, right? You're not stealing
Yeah.
their design or anything.
No.
But there's probably open art on that, so it's probably okay. Also, I know we have some NAPA members, so if you need
Yeah, I'm gonna try to find some, but.
I got a whole roll.
Yeah, we're kind of, I don't know.
I'll tell you what it's at.
Okay.
Our main thing is the catalyst. I think she quoted me like $900 for a little sheet, and I was like,
Yeah, that's just a big job, just getting the platinum electrodes.
Yeah. I can point you to some. I'll point to some websites and stuff that we used to use to get this stuff. There's like some carbon bottles. You get their little less expensive. But awesome.
What do you think was the most challenging thing in understanding this field or the work that you did?
the research paper is 100%, because I walked into this with Google Scholar, and the first thing I pulled up was 25 pages of hieroglyphics, and I spent like probably a week, 2 weeks just trying to decode this one paper and what it's talking about, so I can use those equations for my modeling. I really got a better
For
understanding.
me, I was doing mostly the design of the model itself, and there wasn't any I guess any barricades or barriers for me, but it was just with the 3D printer. We printed some of the wrong parts in different sizes and stuff, so we had to cut back on that and stuff.
Yeah, mass transfer, quite complicated.
Mhm.
I hate it. So I'm impressed that you were able to, I guess, even find data regarding this. I guess it's a well-researched area, but a lot of times mass transfer, like you say, is this, well, we don't really know what's going on, so we're just gonna ignore it. Yeah, mass transfer limited, and then you can just use a different set of equations so that you don't have to worry about it. So that's it's impressive that you guys did that level of research. It's kind of beyond what I would have expected. I should. I wouldn't do it.
And then looking into this project, it was just, I think it was like kind of like Timmy's, where if you get a lot of research papers on it, and you're trying to understand what happens with each part. And so I really wanted, I'll just keep asking question after question after question of how does this work? How does that work? How did you get this equation? How did you get that equation? And so that just led me down the rabbit hole of doing all of this. Mhm.
So, I think looking at the angle of changing from efficiency to trying to minimize costs, I think is a really smart tactic, because you can spend all this money and effort trying to minimize your over potential to lower your electricity costs, but if that makes your cell costs go through the roof,
Then no one's gonna use it. No one's-
Exactly.
Yeah.
so I think finding a good balance of that was really smart.
Well, give him a hand.
Amazing.
It's always cat box, cat box.
All right.
That's what I'm doing. Yes, it's there's all the costs.
What we did. That's right.
Okay, so the last presentation has to do with data center cooling. We're going to take a couple minutes here because man is going to take a little bit of wood up here, right? So just chill out for a minute. Another thing for mentors, so you guys don't freak out. In a couple minutes, we're gonna have a passing period. So I got a new classes coming. They're gonna sit and watch. So we're gonna have about 20 some kids coming here. So, but that is the last presentation. So we're ahead of schedule. So we're good. We're good there. Just a few more minutes. I don't know. I just don't want that class coming in while they're in the middle of presentation.
Oh, so you're gonna wait for that?
Yeah, I'm probably gonna.
We got our points.
It will be this is 4 p 11, 11:50. 11:40. So 5 more minutes. They're gonna start coming in.
I'm thinking about going
going back to this site on the left. So that'll be our second point. That is unless we have a flat capture. I gotta see if I can get transportation. That's what I can get
I'll make sure I'm not as busy.
And it's not hard. Next year, y'all starting to see this year.
I want to take this chance here for our visitors, EDP 2, right? Raise your hand. So, this is going to be, if you decide to press on with engineering and you're a junior, this will be your senior class. It is fully into projects. First couple months, we go through certain things like ethics and engineering, and we see some project management things. But the main, and safety, of course, you all know about safety. Then after that, these gentlemen have been very gracious to give us time to mentor and provide projects. We this year have about 7 or 8 mentors and about 16 projects. And so this right here will be the final presentation for some of the projects. Other projects, like for example the rover, I don't know if you guys were here for that one. It's gonna continue. Like they're gonna work on their steering, it's gonna keep on going. Different phases. Other projects will end and then they're gonna start another project. And actually we have one project that is being, it was submitted by one of our students that wanted to do that kind of project, made a proposal, we're working on producing that. So again, the idea of this class is for you guys to get a real deal with the industry. These individuals are chemical engineers, they're scientists, and so you get to work with them once a week. You meet them on Zoom, and you just keep going with your project the same way that you're learning in EDP2 with Mr. Jordan. So the idea is now this is a cherry on top. So that would be the question, why do I want to take this class? Why should I take this class? And the main reason is the networking, the experience. We are mimicking what a senior would do in engineering school, which is a design review on a capstone project. That is the idea here. The rubric that they're using is coming from UTSA, the Department of Engineering, for their senior projects. So again, it's giving you a little taste of what you're gonna encounter if you go to college for engineering. Okay. Like I said, we're gonna have a flux of about 20 kids here coming in, and then we're gonna start the process as soon as the bell rings. Okay. So hang in there. I know last project was super deep, right?
Yeah.
But I mean, just look at what we're doing. We're trying to come up with a fuel for rockets. All right. So again, this is the kind of thing that you have to do. This is what these gentlemen do on a daily basis in the research that they do. So again, that is the idea here, to expose you to these things. Believe you me, Victoria, like she said, when she started, she was like Chinese, right? And it's just a matter of how bad you want to learn. And so she went in there, and with the help of the mentor, we came up with the solutions. And now, I mean, I thought I was looking at a chemical engineer major here. You guys agree?
Yeah.
I mean, I'm talking shop with these guys. So again, it's an amazing experience. That's the advantage of taking this course. You don't have to go as deep as she did. You're gonna see this project coming up super cool too. Literally cool. And so it's just a matter of what you like. Okay? Oh, thank you. Got it. So yeah, just come on up. Do we have any more people coming here?
Just
yeah. A few more minutes and then we start. You guys are ready? You got your clicker? So if you guys have any questions about this class, you can talk to Mr. Durham or myself.
Now we have find a mentor and we printed prosthetic
What is it? It's called tools.
I mean, I'm not making money right now.
All right, one more minute. Yeah, but I'm not asking you guys to do a little how you feel. can. You don't have to be all the way up there. Just come on up closer so you can listen to what's happening. Okay, last presentation for this is gonna be data center cooling. Super cool presentation. I can literally write it. And so, further ado, go ahead.
Hello everyone, my name is Adrian. I'm Blake, and this is our data center cooling project. So a short product description, the purpose of this is to produce a product that cools down either servers or PCs, and we decided to cool down at the circuit level since that would be the most efficient. This product is geared more towards people who already have their own PCs or people who have like a small handful of servers, not necessarily gigantic server rooms. So this is our short timeline. The first beginning, the first couple of weeks, we were doing brainstorming, notebook sketches and all that, our bill of materials, whatever was necessary. And at the end of the month, we started doing our heat calculations in our small prototype. And by prototype, I mean we stuck the Peltier to a fan just to see how much it would heat up. This is the last couple of weeks, more heat calculations, a prototype change, more powder arrival, soldering, and then finally systems. So this was our preliminary Gantt chart. This allowed us to, divide up tasks between me and the lathe and see, get everything done. So a short explanation of the Peltier effect. So how it works is a current is ran through a thermocouple, and that causes heat to be exchanged from one side to the other. So the Peltier chip is made of P and N type semiconductors. The N type semiconductor has a bunch of free electrons, and that is the side that faces the CPU. And the P type semiconductor has a bunch of holes that, when a current is ran through it, the electrons will keep trying to go over to the other side. So that P-type one will be the hot side that is facing the fan, and later on the aisle. So yeah, that is how that works, and it is quite a potent process because we left our Peltier powered on for about 3 seconds without cooling. It got to like 100-something degrees and it instantly melted the plastic that it was on. So it is quite some product benefits. You could do this one.
So air coolers usually keep the CPU fan at like 104 to 185 Fahrenheit per load, especially on higher loads. We believe that we can get it down to below freezing because typically they can get to around -20 Fahrenheit, but we're aiming to keep it around 45 because if it gets too cold, it will cause condensation on the board, causing a short circuit, but we also added a backup for that by spreading Vaseline around it to prevent moisture from making contact. It's also a lot cooler because we have 2 fans and they can be a lot bigger because they don't have to be held within the case right above the CPU, and usually there's a height limit right there. And this will impact the performance positively because we will be able to overclock the CPU by lowering the temperature drastically. Here is a sketch model. As you can see, we have the AIO right here, the CPU is here, and the power supply is here. This is an input switch to power the power supply to the Peltier chip, and that's going to be controlled with a MOSFET. So this is the bill of materials. We have our MOSFETs, thermal paste, the power supply, Peltier chips, the extension cord. We were using that for wire. A power strip, the liquid cooler, the PC case, and the inlet plug. This is our color-coded model. The wires, the orange is power, the blue is circuit boards. This is the water lines connected to the CPU.
And yeah, we made this color-coded model because of feedback from some of our classmates, because our original one, as you can see, all gray, you can't really tell what's happening. This color-coded model makes it a little easier to understand everything. So these orange wires right here are where power is flowing through. That cube right there, these are the MOSFETs, and then you can't see it very well, but that little square underneath this is the Peltier. And obviously water keeps connected to fans, all that water is constantly getting cooled down and sent back to Peltier. We were going to connect our product to a monitor and check the temperature of it using built-in sensors in the motherboard just to see how hot it was. And that did work pretty well. We needed to install some extra software, but that wasn't too big of a hassle. These were some old calculations. This 1000 watts right here was heat transfer that was using the CPU fan previously. It was able to get a heat transfer of about 1000 watts. And this was the heat transfer using our IO cooler, which was about 30,000. So this tripled the efficiency of our cooling, and it allows the Peltier to get a lot colder without necessarily being able to cause damage. An oversight that we did do, which is this right here, victim number 1. We did not factor in the increased amperage needed to needed when switching from a fan to an IO cooler with a pump. And this old power supply was only 1 amp, so it could not handle the stress and it short-circuited and it burnt out. It was very funky smelling, so we opened it up and threw it away. This cost about $15 worth of damage, but thankfully that was the only thing damaged. No other wires or nothing else was damaged, so we just needed to order a new power supply, and that did cause about a week's worth of delay ordering a new, more amped up power supply. This was our new power supply. It was 3.5 amps and 12 volts, and this finally allowed us to begin our testing since we hadn't been able to power our electric power. So soldering, Glade did a bunch of the soldering, and we'll explain that right now.
So a lot of the tips, they were connected, but since I hadn't soldered them previously, there wasn't a lot of, like, the connection wasn't very good, so it caused resistance because sometimes they would fray and only like little bits of the wire, and they weren't able to carry all the amperage. So I had twisted them together much better, and I actually applied solder and flux, which made it to where the current was allowed to pass through much better. And then I also used a MOSFET, which the way a MOSFET works is you have the sustained power going straight through, and then you have a lower voltage system that is completely separated from the high voltage, and that is acting as a switch to enable this power to go through. This is what we would connect to the motherboard, telling it when to turn on and off the fan without us frying the motherboard by pushing power directly through it. And then this is our new power supply. It is 5 amps because the fans were incredibly slow and they were actually kicking because it would constantly try to do over voltage protection and then immediately turn off and then try to restart itself over and over. And then our backup is the Vaseline I was talking about, because if it gets too condensated or if for some reason the MOSFET fails and it constantly keeps running, the moisture won't be able to make contact with the board around where it would accumulate.
Thank you. And these were some movie calculations, optimistic and realistic. If you want to know, this is the optimistic part, is 27.8 degrees Celsius. That is the change going from 7 degrees Fahrenheit to 20, which is about how cold 1 Peltier chip can get, which is what we have. And this is more realistic, 13.9, going from 70 to around resting at 45. Since, you know, CPUs, since we're doing a whole product on them, you can understand that they get quite hot. And realistically, the Peltier chip probably wouldn't be able to get the CPU down to 20 even if we tried. You could theoretically get more Peltier chips and make a more bulkier system, but that wouldn't be very cost effective and it wouldn't fit needs. So we decided to settle for 1 Peltier chip. And this is our testing results. The average temperatures were slightly higher than our prediction, but we're still great. I let it idle around for about 5 minutes, and it averaged, Core 0 got 50 degrees, and then Core 2 got 48. So that is much better than other competitors like the air fans and regular water coolers and all that. And this is our testing results for the benchmark test. Our temperatures were under 100, so we were pretty satisfied. Core 0 against 77, and Core 1 was 75. So this was a lot better than expected, surprisingly. Because I was expecting it to reach around maybe 90, but this really surprised me, and it's a welcome surprise. Undercutting my prediction by about 15 degrees, which is nice. Comparing cooling, the average temperature loads for other water coolers under load were about 104 degrees, which is why I wanted to beat that 100-degree mark. And our cooler average was 76, so I considered this project a major success. This was our final Gantt chart right here. As you can see, color photos nicely know that this kept us on track for everything. And the deadline extended by about a week and a half, 2 weeks, but other than that, it was great. And thank you for your time, and a special thank you to Mr. Eli Flores for being our mentor. I really appreciate the time that you sacrificed to help us with this.
Can you go back to the Peltier chip? I just don't understand what that mechanism is. If you can explain it.
The one right here, yeah. So
Actually, the one, well, perhaps the one prior. Yeah. Like, what is this effect? Like the base theoretical effect